Okay, hey and welcome to our 11th tutorial in the destruction series, and in this one I'm gonna show you guys how to make this. Actually more like this, sorry. But yeah, kind of how layering of different materials work and how to get a more sort of complex breaking structure. Like this, like breaking a brick wall, for example. So basically we're gonna have to take a look at all the different elements that this includes and how to set them up to efficiently work with each other. So all the elements we're gonna use in this is these. I have merged them together here. It's all of these things. Let's go over them one by one. So I'm gonna merge them here and I'm gonna ghost this and I'm gonna go through each element. So the first one is the outer drywall, as you can see here, the gray one. This one is simply a block that I have made into volume. I've sketched some points. I made a Warner fracture. Again, this Warner fracture is not that detailed. It's just to show the concept of this. You can obviously break more pieces. You can cluster it. You can go more in depth with where you scatter the pieces. I'm going to show a version at the end of this tutorial how that will look. But for now, we're going to work on a really basic geometry. We're then going to do a connectivity thing because we're going to want to create our own name attribute. Remember, there's a name attribute comes out that is called pieces. If you check here, all the pieces of this has a primitive attribute called piece 0, piece 1, piece blah 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 blah, up until piece 99, because we have 100 points, 100 pieces, and therefore 100 different piece attributes. We are going to want to create our own piece attribute, and I'm going to tell you guys why in a minute. But we need to create the attribute called class. And to create a class for each of these, we're going to use a connectivity node. The connectivity node simply looks at each of these primitives and looks at who shares a vertices. If a primitive shares a vertices with another primitive, it's going to be put in the same class attribute. The class attribute works similarly to the name attribute. It is a point attribute though, and it gets a simple integer for the class attribute. So the integer is 0, 2, 3, 4, up until 99. So the same pieces that has the same piece attribute has the same class attribute. That's a very important thing. So we're going to use the class attribute to create our own piece attribute later on. Yeah. So what we want to do then, we want to promote this class attribute from a point class to a primitive class, which means that now this class attribute is not going to show up in points, it's going to show up in primitives. So here we can see that every primitive that has a class attribute of 0 has a piece attribute of 0. Every primitive that has a class attribute of 99 has a piece attribute of 99. So that kind of correlates very nicely like that. I'm actually not going to go over why we do this right now. I'm going to create all the elements, and then after that I'm going to tell you guys why this is so important. Because remember that we have a class attribute now that we are going to use to create our new name attribute. So I'm going to disable this attribute wrangler right here where I actually created. It looks like this. I'm going to tell you guys why later. But for now, we're just going to take a look at how to put it into a simulation and get it to work. So then we're going to just go through the similar things that we've done to previous tutorials. We're going to start creating our network for constraints with the connect adjacent pieces. We're going to connect and put connection type to adjacent pieces from surface points to get this kind of pattern, which is nicely going to work with these kind of pieces. We're going to create our attributes called constraint name, put the string to glue, and constraint type to all. We've done this before, so you should be familiar with this, but yeah. Then we're going to use the assemble sub to pack these pieces. Again, nothing new here. We're going to just tick this box, create packed geometry, which means that we now have 100 packed fragments. Then again, we're going to start grouping the bottom points or pieces. We're gonna set the bottom pieces to inactive and the top pieces to active. So we have like an anchor down here. And then we're gonna out this geometry with this null called out pieces 4 that we later on gonna see in our .NET. Same with the constraint network. We're gonna put here out constraints 4. We're also gonna recognize that in the .NET. So this was the outer layer of the brick wall. Now we go to the inner wall. Exactly the same method here. Same amount of pieces, 100 pieces. Want to fracture it, pack it, group it, set to inactive, all that jazz. Same here. The connect adjacent pieces to create a constraint network. Same with attributes on the attribute create, and both same outs. Then we're gonna go to the brick wall. The brick wall is a bit different. We are first gonna create a single brick, move it off to the left a little bit, and put it to a decent scale. And then we're gonna copy it with a copy stop. We're just gonna transform it like this, create multiple instances of it, and then we're gonna copy it once more in the y direction like this, create 15 copies. So you have a nice brick wall like this, very procedurally created. And since these are already, they are not packed, right? So we're gonna pack them. So now we have 180 packed bricks, basically. And we're gonna create a name attribute here. That's very important on these assembles, by the way, to uncheck this create name attribute, because that will kind of mess things up. So definitely keep in mind that on these two, we wanna not create a new name attribute. We wanna keep the one from the warning factor, or in this case, create our own. We're gonna get to that in a minute here. Regardless, here we actually do want to create a name attribute. We're gonna keep this checked, create name attribute, which means that these will not only get packed, but they will also receive a name attribute here. So the names will be piece 0 to piece 179. Great. Then we're gonna do connectivity. We're gonna create class. This is also for the same. If we want to create our own name attribute, we're not gonna do this for these actually. It's not necessary, but we could do it. So this is just in case. It's gonna create a class attribute the same way as it did before. So the piece that is the pointer is 41, get the class 41, and the piece name attribute is piece 41. So that kind of coincides as well, very nicely. Then we're gonna go ahead and create our constraint network. A little bit different this time. We're gonna use the connection type adjacent pieces from points to get this more like brick kind of structure, because bricks can only connect in 4 locations, right? A brick can maximally connect to 4 other bricks, which basically works really well for this kind of shape. If we did put it to this, it wouldn't even work. And this is not that efficient either. So the first option here is definitely the one we want to go with. These, don't really mind them, it's fine. We want to bump the maximum surge point up to 1,000, just in case. Minimum, we can put it to, yeah, let's put it to 10. That's fine. Max connections, we could put it to 4. Just in case, I'm going to put it to 5 to get that extra step of it. Since the actual maximum connection for a brick can be 4, we can put it to 5. And then we're going to create the same attributes here. Constraint name, put it to glue. Constraint type, put it to all. Same as we've done before. And that's it for the constraint network. Just out that here with a null, and then we're going back to the pieces. We're gonna group the bottom layer of pieces like this. As you can see, they're grouped here. Again, we're gonna create them inactive to create an anchor with this wrangle here, as we've done in several tutorials before. Then we're gonna out the pieces here with a null, so we can locate them in the .NET, and that's it for the bricks. Then we're on to these guys, the beach toys, basically. We are gonna create 2 of these, just a static object that is gonna be in front of this wall to kind of collide with it or fly into it. We're simply gonna transform them to a good location. We're gonna pack them with a pack stop, like this. So now we have these 2, where we have 2 packed geometries, and we're gonna out that, like that. And then last but not least, we're gonna create a ball that is gonna collide with everything. This is gonna be our active RBD. That is actually just a polygon transform it a little bit, scale it up a little bit, and then out sphere 2. So now we have all our elements here, and they look like this together. So our wall, drywall, inner, outer, bricks, static, breach choice, and our ball. So that's all our elements. Now, again, as you remember, this is still unchecked, because this is a trick that is very essential to having multiple elements in a sim with working constraint networks. I'm going to get to that once we see what's erroring. But for now, we're going to just chug this into a solver in the .NET and see what's going on. So let's dive in here. So, well, in here, I'm going to go ahead and unhide all of these. Let's see what we have here. So, we're going to start off here. So first of all, we're going to bring in our bricks like this with RBD packed object, not RBD, RBD packed objects. We're going to bring it in. Locate it. That's it. Just check so the guides works fine. They seem to be alright. Collisions should be okay. Display object again. So they look like this. Then we're going to bring in our, let's see if this inner outer. This seems like the inner. Let's actually rename this. It's always good to rename things, guys. So, then this is the brick wall inner. Let's just see that everything is working. It seems to be all right. It's always a good practice to check if the actual bullet data or these holes are looking proper. And I definitely do here, so that's perfect. Usually the Warden Fracture actually does a really good job of that, so it usually is fine. So we have located here in the subpath as well, so that's imported. Then next up is the drywall. No, actually these are the baiting toys. I'm gonna call this toys. Let's just check that they are working fine. Again, these are kind of more like simple shapes, but that's fine because we're not gonna do anything super complex with the collision of these. We could put them to concave, which will take way longer to calculate, but it's also more accurate. So now they can collide here instead of putting to a convex hole, which kind of creates a hole around the maximum points of the shapes, basically. But these are fine for now, and it's going to be very fast to simulate, so that's great. Let's display them again. Now the outer wall, outer drywall. Let's call this drywall outer. That seems fine. Let's just double check. Also good practice. Yep, that's cool. And then the ball, where is it? Here. This one is fine. We're just gonna put some velocity to this one, so it kind of springs off and shoots into the things. So we're gonna put a minus 26 in the X direction. It's basically gonna shoot this direction. And then we're gonna merge all of these like this. Just merge all the things together, chug them into the bullet solver, and we can already now start playing it and see what happens. And that looks quite cool, actually. It's like a space explosion almost. I don't know. Regardless, so we see that everything is working fine. The collisions are working pretty good. We have some velocity on the sphere, and that's it. Next up, we want to bring in all the constraint networks. So we are going to go ahead and hide these by clicking this grayish brown button on all of these. And then we're going to go to this one. This is going to be our bricks. We want to import them. Find the null that points to the constraint we created for the bricks here. Create a glue constraint relationship. Put the data name to glue, since that's the name of them, like the name of the primitives. And color it red. Seems like it's working. We can play it just to see if it breaks, and it does. So that's great, perfect. Next, we're gonna import the drywall inner or out. We're gonna color these blue. Find the null that they are pointing to. In here, we can define the strength a little bit. These strengths you always want to play a little bit with. I'm gonna put it into default for now, but you can definitely play around with them if you want stronger or looser constraints. Again, put this to blue so we can kind of differentiate. So now we have two constraint networks in here. Then we're gonna import the outer or the front drywall constraints. Color them green. Put them to some strings you want. And just to check if it works, we're gonna see if they break once the ball hits them, and they do. Actually, to visualize that, we can do like this. Boom. Actually, it is not only the ball that hits them, it's the toys as well. But regardless. Next up, we want to create a ground plane like this. Nothing fancy. And then some gravity to bring it back onto Earth. And that's going to look like this. Not that fault. Anyway. Next up, we are gonna enable all of these again. And we're actually gonna run this sim. Let's run it. Boom. That's cool and fine already. Like it's quite okay. And it's kind of cool that this piece actually falls off here, which is like interesting, I guess. But something is wrong with this simulation. And I don't know if you guys can tell, but from this it looks great. It looks fine. But here, if we go and we play it, these pieces start to fall. And that is because, I'm sorry, I'm going to go ahead and disable this again. For some reason, this back constraint network doesn't seem to hold them up. And that is because the name attributes of these two are the same. They are like, this .NET finds name attributes for these pieces, and they are the exact same. And therefore it doesn't know where the constraint should be connecting and what piece should be connecting to which piece. And that means that we need to offset the name attribute for either of these, so they don't have matching name attributes. And how to do that is exactly what I did here before. So this one we can leave it alone. That's fine. We cannot leave this as a name attribute that comes out of the warning factory. We're not going to do anything with it. But on this one, the first drywall, we are actually going to create our own with the help of the connectivity here. So we have promoted the connectivity class attribute to a primitive. And in here, instead of having the name attribute be piece 99 from piece 0 to 99, we're going to offset this attribute by a really high number. So there is no way for it to be the same as this one. And how we do that, we actually need to create our own name attribute. It's easier. You can offset the actual name attribute that's already there, but it's kind of clunky to work with strings most cases. So I like to create my own. So let's remember we have a class attribute that is very nice, and we can create our own string with that. So what we're gonna write is, I'm actually gonna rewrite this. So I'm gonna delete this, and we're gonna put what we're gonna create a string called name. That means we're gonna type s at name equals, in these like brackets, that's how we define the first part of the string. We're gonna call it piece, like that, and we're gonna plus. And this is another like really weird expression in Vex that is like, you just have to know it. It's called E2A or I2A, integer to attribute. So what this does, it adds an integer onto a string. Because right now we actually do have a string called piece. You just have to do these, and now we have an attribute called string, piece. So the attribute that we have now, that's called name, is just piece for everything. We want to add a number that is in unique for each connectivity class attribute. And how we do that, we put plus I2A E2 ITOA in parentheses at class. At class. Boom. And there we go. We now have our piece attribute. And we now have created it by ourselves, which means that we can now add any value at the end of this. So we cannot put plus, I really like just a seed number, which means that now our piece is gonna be a very high number here. But that's exactly what we want, because now nothing will correlate with this. We will not have any piece that is piece 0 or piece 55. We will have a piece that is called piece 2,003,000, whatever, like a really high number, which doesn't exist here. Instead here, all the piece attributes are from 0 to 99. There's other procedure ways to do this, to actually like recognize what pieces are here and like kind of add that on top here. We're not gonna do that now. And obviously if you wanted to, you can simply go ahead and do this. You could add, instead of this weird crazy number, you can know how many pieces you have in other. So you know that you have 100 pieces here, which means that if you add simply 101 here, it's gonna be fine. So instead of going from 0 to 99, you go from 101 until 200. So that's fine too, like as long as it's an offset, I guess. Anyway, after we've done that, everything is gonna stay the same. Nothing changes. Only this attribute is put to these constraints and the pieces. So now they're gonna be not matching anymore, which means that our sim is gonna work totally fine. Let's go ahead and hide these, and let's play the sim and check the back, and voila, it's now working very nice, and nothing is falling prematurely, and all the collisions are working perfectly. So that's a really cool way to do it, to work with many elements and have like static and kind of RBDs and stuff like this work together. The next step to this is obviously to connect the actual drywall to the pieces, to the bricks. That's a bit overcourse though. We might do a tutorial later on that, but yeah, you can definitely get some really cool results with this. So yeah, I'm just gonna let this play for a little bit so we can see the whole thing and kind of what happens. Yeah. And I like how the bricks are falling here. Poof. Anyway, that's it for this tutorial. I hope you guys learned something. And I'll see you in the next one. Thank you for watching.